Here's another problem about shooting baskets. We're continuing with the situation from the geometric distribution video. So we've got a basketball player who typically makes 70% of his foul shots. We assume the attempts are independent. We're going to find some different probabilities, answer some different questions from the other video. We still got Bernoulli trials. And remember, these are the characterizations for Bernoulli trial. There's a yes or no each time, success or failure. I guess in the modern lingo this would be win/fail. And there's the same probability each time, and we're assuming they're independent or very close to independent. But here's the difference. But the binomial probability model, it's not that it's a different situation, it's that we're asking a very different question. Instead of letting somebody make these foul shots and not predetermining how many they make in advance, but just letting them go until they make one, we're actually going to say in a fixed number of tries how many successes. We're not going to stop after the first success, but we are going to stop after a given fixed number. So this is an input to the model that we have that wasn't present in the geometric model. In a different video, probably, I'll talk about why this is called binomial. And that's a term from algebra, and it's kind of obscure why this would apply. But there's a very neat connection, but we're not going to focus on it in this video. Okay, so here's the kind of probability that we want. The probability that he makes exactly 2 out of 4 foul shots. Notice the exactly. We're going to be dealing with like at least in some other versions down here, but the basic binomial probability model applies to exactly. What's the probability of making a certain number of successes out of 4 possibilities? Okay, so here's what would be easier to answer with our basic probability knowledge. Okay, the probability of, let's say, that he makes a success and then a failure and then a success and then a failure. Okay, and here notice always we have to figure out what is success and what's failure. Let's say success means making the shot. Okay, which is what we did most of the rest of the other video, but not every part of the other video. Okay, so this would be the probability of a very specific pattern of wins and fails, of successes and failures. He makes a shot, then he misses one, then he makes one, then he misses one. That's one way that he could get exactly 2 out of the 4. Okay, well, this is exactly something that's answered by our fundamental probability principles, because it's an and. It's success on the first and failure on the second, and success on the third and failure on the fourth. And they're assumed to be independent and the same probability each time. Okay, so this is going to be the probability of a success on first, I'm kind of mixing my math modes here, times probability of failure, it doesn't really matter if that's on math mode or not, does it? On the second, times the probability of a success on the third try, times the probability of failure on the fourth try. Okay? And it doesn't really matter that it's on first, on second, on third, on fourth, because of the assumption of the same probability each time. Okay? So that's going to equal just the probability of success squared, because we got 2 of those, times the probability of failure squared. We have names for those. Those are called p squared and q squared. Okay. So, because there's 2 successes and 2 failures, it's just the probability of success squared times the probability of failure squared. Very simple, but not the question we were actually asking. This is only one of many ways that he could make 2 out of the 4 foul shots. You probably, in a lot of these situations, you don't necessarily care which ones were the ones he made, which ones are the ones he misses. It's a situation where the score that he gets out of this is just the sum of how many times he succeeded. And so we only care about the sum. It's a very typical case. And we'll see that it translates into some very important statistical principles later. So if we only care about the sum, then this is one of many disjoint possibilities. We also need to consider the probability, let's not use math mode actually, it's annoying me, of, let's say, fail, fail, success, success, and probability of fail, success, and, okay, well, so we obviously need to know how many of those there are. That's going to be the last piece of our puzzle. But if we could figure out how many there are, we're going to be set. Because notice this guy. The probability of fail, fail, success, success that's just going to be p squared q squared again, okay? Because it's got two successes and 2 failures. It didn't matter what order these were in, because the probabilities are always assumed not to change from time to time. Okay, this is another p squared q squared, okay? So all of these in the different orders are giving me the same amount, the same probability, and they're disjoint. If I look at SFSF, that's a very specific situation. If that happened, this did not happen, the FFSS, and this did not happen. They're all mutually exclusive disjoint possibilities. Oh, that's great. That's where the sum rule comes in. I love this example. I love binomial probability because it brings together all of our rules. We've used the multiplication rule for independence and we're now using this sum rule for disjoint and or. Okay, so it's going to be the sum. So the total probability is going to be the sum of some number of copies of p squared q squared. Okay, alrighty. So let's just give a name for this. Okay, there's a couple of names that people usually use. What we're looking for is the number of ways we can choose. We've got 4 slots, the 4 shots. And we're looking for the number of ways we can choose 2 of those slots to be filled with S, and then the others are going to just be filled with F. Okay? And so the notation that's preferred in this book is this funky notation. It's parentheses. It's kind of like a fraction because one thing is on top of the other, but you don't put a bar, but you do put the parentheses. It's called 4 choose 2. And we're just going to multiply that by p squared q squared. So this is going to be a number we still have to figure out. It won't be that hard. It's just going to be an abbreviation for how many ways can you have 4 slots and fill 2 of them with something you're interested in, namely which ones are going to be the S. Because here this is a different way to fill those 4 slots with 2 S's. This is yet a different way to fill the 4 slots with 2 S's. Okay, there's another notation that's used on the calculator, which is this one. Ooh, let's see. It doesn't work very well. Actually, let me put it here. For some reason, it doesn't work very well right after an equal sign. Okay, so let me just put it here. Also known, not jown, known as 4 choose 2. So you read this as 4 choose 2. You also read this as 4 choose 2, even though it's not as obvious without the C there. Okay, so I've given a name to this thing, but the trick is I haven't given you the number. Okay, so let's figure it out. And then I'm just going to tell you kind of a master formula. For this example, we can figure it out. What we're going to do is we're going to look at just an abbreviation for all these different ways we could do it. Okay, we're taking 4 objects, namely the slots 1, 2, 3, 4, and we're picking out which ones are going to be S's. So we could abbreviate this one as 1, 3. Okay, and let me just put commas. Okay, I put the S's in the 1 slot and the 3 slot. So success on first, success on the third. This one was 3, 4. Success in the 3rd and 4th slots. This one was 2, 4. Okay, what we need is a systematic way to list all those guys and then count them. Okay, so in this example, we can actually just list it out. Okay, let's see. 1, 3. Why don't we start with 1, 2? Because that seems like the reasonable place to start. It could have been success, success, then fail, fail. Okay. Then 1, 3. Then 1, 4. Okay. Then it could have been the 2, 3 slots, or the 2, 4, or the 3 slower. The 3, 4. Okay. Looks like there's only 6 ways it could have happened. Okay. So this, in fact, is going to be 6 p squared q squared. That's, in this example, that's 6 times 0.70 squared times 0.30 squared, and finally we're going to get an actual answer, 26%. Okay, about 26.5% of the time he will make exactly 2 out of 4. It seems reasonable. If making 70%, we kind of expect more likely to be he'd make 3, but it's not at all unreasonable that he'd make exactly 2 out of 4. Okay, so in this case, we could just brute force it. We could just list all these guys. Okay. In the next example, it would be much harder. Okay. We've got 10 slots to fill. So the numbers 1 through 10. And how many ways can you pick 7 numbers out of 1 through 10? It's a lot more, and I wouldn't want to have to try to list them. Okay. So Let me just give you, without, hopefully I'm not making this video too long, let's see if I can give you a little bit of an idea of how to be even more systematic here. Okay, so one thing that's going on here is that I didn't have to list 2, 1 or 3, 1. Okay, if I'm just saying which slots are S's, if I say, oh, the second slot and the first slot, or like here, let's look at this one. This is where 1 and 3 were S's. If I said, oh, the third slot and the first slot were both S's, that's the same thing. It's the same situation. But I'm going to be a little perverse here, and I'm actually going to go ahead and list those all out. Okay, so here's what I'm going to do is I'm going to make a little table. Let's insert, oh no, actually, let's just make it a matrix. Okay, and I'm going to make it a little 4x4 matrix. And I'm just going to put down all the possible ways to put these numbers together. Okay. Okay, that's a very systematic, easy thing to do. And notice there's just 4 squared. There's 4 times 4 ways to do that. Okay. Now, there's 2 things that are wrong with this this table. One is that it counts the doubles. Okay. We definitely wouldn't say, oh, he got a shot on the first slot and the first slot. That doesn't make any sense, and it certainly isn't 2 successes and 2 failures. Okay. So we want to kill these guys. Okay. And now we've got something that is not the answer we want, but it's very easily related to the answer we want. We just wanted these guys where the order didn't matter. Here, I'm counting the ways to pick 2 things, from 4 numbers, with the order mattering. Like I care a bit about the difference between 1, 2, and 2, 1. I care about the difference between 1, 3, and 3, 1. That's not the right answer, but notice there's a pairing here. I'm listing the 1, 2 possibility exactly twice. I'm listing the 1, 4 possibility exactly twice. Everything gets listed twice. Okay. So here's why that's so useful. Okay. We take 4 squared and we subtract the doubles. Okay, there's a better way to write that. That's 4 times 4 minus 1. Okay. That's with the order. That's counting with order. It's not what we wanted, but it's more systematic and it's easier to do. Okay. Now what do? We just divide by 2. Because everything appears exactly twice. Okay, and so what we're getting here is 4 times 4 minus 1 all over 2. Okay, or 4 times 3 over 2. And that exactly is the 6 that we got just by brute force listing. Okay, so this is an example of how we could have been more systematic about it. And in fact, it's going to give us the answer if we choose 2 slots without caring about the order from n total slots. The same idea is going to happen. It's going to be n times n minus 1 all over 2. Okay. Now the question is, what about choosing some other number like k slots from n total? Okay, and I'll save that for the next video.